So last time, we talked about blocking flows. And we started, we proved a lot of things about them, right? Each block increases the distance between the source and the sink. Each blocking flow calculation increases the source between the distance between the source and sink by 1, and so n blocking flows suffice to find a max flow. We discussed some special cases for unit capacity graphs where root m blocking flows are enough to find a max flow. But basically, we homed in on just how quickly can we find a blocking flow. We talked about how blocking flows involve a combination of advance, retreat, and block steps, right? Moving forward along a residual edge, moving backward along a residual edge and destroying it, or augmenting along a path that you have found from the source to the sink. We argued that the advance work is smaller than the block plus retreat work, because every time you advance along an edge, you've essentially committed to either retreating along that edge or sending some kind of flow through that edge. So in order to analyze the time that it takes to compute a blocking flow, all you have to do is analyze the retreat work and the block work. We also argued that the retreat work in a blocking flow algorithm is always order m, because when you retreat along an edge, it's because you know that it is no longer possible to send any flow to the sink through that edge, and so you can delete that edge, right? So there's only one retreat per edge. And so all of the work that we had to do was around the time that we spent on the block step, right? And in unit capacity graphs, we argued that this was, again, order m, because you would only block an edge once, and then it would be destroyed, and you wouldn't encounter it ever again for future block steps, right? More generally, we said that when you do a block, you're sending flow along a path, and that path has length at most n edges, right? And each time you do that, when you send a unit of flow along the path, you are increasing the total value of your flow by 1. And that means that as long as, talking about the integer case, you're going to do at most f of these block steps over all the blocking flow steps. Right? Whereas in the unit case, in the retreat case, the O of m work is per blocking flow phase, right? But we put those two things together and said that the retreats are order mn over all phases. And so then we put these two observations together and found out that our overall runtime was order m plus f times n in integer capacity graphs. We then said that for scaling, right, each scaling phase introduces at most m flow in terms of the capacity that you add during the scaling phase. And that means that f is equal to m, and that gives us an order mn time what did I jump over here? Order m plus f. That's what I get for not looking at my notes. One sec. Yeah. So it's order mn time per phase. And therefore, overall, it's mn log u time. Okay, so that's how we finished up last lecture, right? I redid that because I got some good questions about it after the lecture. And so I'm going to encourage you again to ask your questions during the lecture. Right? Remember that one of the main benefits of asking me questions is that it prevents me from covering more material. So it saves you from getting confused by the things that I end up not covering until the next lecture, when hopefully they'll be less confusing. Where this leaves us as a sort of summary is that in the unit capacity case, we have a simple order mn time algorithm, just any old max flow algorithm. In terms of scaling, we can now achieve order mn log u, right, with blocking flows, which again has this mn in it. So, and right, this is sort of a natural progression from unit to scaling, even though the technique that we use here is rather different. But then for a strongly polynomial algorithm, for this we use shortest augmenting paths, which has an order mn squared running time, right? And that's a pretty big that's a pretty big difference, okay? Sorry, this is still blocking flows, not shortest augmenting paths, but it's a lot slower, okay? And so the question now is, do we really have to pay this extra factor of n in order to get a strongly polynomial algorithm, or can we get closer to the mn time bound that seems to emerge in the unit capacity and in the scaling cases, okay? And so for this, it turns out that we can, and the trick is to think about data structures. So if we go back to the sort of general framing of blocking flows with advance, retreat, and block, right? Let's think about how that plays out as we do a blocking flow calculation, right? We start at the source, and we start exploring along some path. Maybe we hit a dead end, we block and retreat and so forth, but we back up. And eventually, from the source, we reach the sink, okay? And let me make it a little longer. We now can do a block. And if this is a unit capacity graph, that block is great because it destroys all of the edges on the path, right? But in the general case, we're blocking and we're only saturating a single edge that gets destroyed by the blocking step. And we haven't saturated all of these other edges. Nevertheless, we go back and we've just finished a block step, so we start over again at the source and we start exploring all over again, right? And the retreats are paid for, but essentially we are going to possibly be traversing these edges again the next time as we're exploring. We're going to sort of do a second advance over the same edge. And this is why we have to sort of charge the n work of this blocking step. Basically, all is associated with the deletion of this single edge, and it becomes very expensive, right? But maybe we can think about data structures that would save us this work, right? So if you think about it, after we have done this exploration and done this block, right, there's a lot of information here that we can still use for continuing our blocking flow calculation, right? So again, in our naive use of blocking flows, we go back to the source and we start exploring over again, right? Now, I would claim that starting to explore all over again is wasting information that we still have, right? What would be smart to do if we're in this situation, we've just destroyed this edge, and we want to look for our next blocking flow? How could we leverage what we know? Yes?
You start from like the last node, like the node on the edge, which was the bottleneck.
Right. So I could start right? The point is I blocked and destroyed this edge, but this is a path of available edges with capacity. So why didn't I just start exploring from here instead of starting from all the way back at the source, right? So maybe I'll try another pathway, right? And I'll find another path to the sink, right? And now I can do another blocking step, right? And that kills another edge, right? Maybe I'll explore, and now again, I can do the same thing, right? I can explore out from where I was. And one thing that might happen is that I might actually reattach. Like there's some other available capacity or some other paths or partial paths that I could kind of hook onto, right? If I discover, oh, I'm on this vertex, well, I've already mapped out that there's a path to the sink from this vertex. So I don't really have to explore. Just as over here, I sort of jumped from the source to the head of this path, right? If I manage to hook into another path, I can jump to the head of that path. And maybe the head of that path is the sink. Or maybe it's someplace else where I, blocked something, right? But there's this sort of sensible idea of maintaining this partial information and hooking together these partial paths instead of actually doing an entirely new blocking flow step. So if we flesh out that idea, as we do these explorations, we're going to create a bunch of these partial paths. But if you think about it more carefully, what they're going to be are what we're going to create are trees. Okay, so we're going to maintain a forest of indirected trees. So in one part of this graph, I'll have a bunch of edges that still have capacity. That I can use in building my next augmentation, okay, my next blocking step, right? I may have several of them because things have gotten detached in the blocking steps. Various edges got deleted. And so I've got lots of little bits of trees floating around. Okay. Now, as I explore, I'm on some vertex, which is in some tree. But since I'm in a tree, I know there's capacity all the way to the root of that tree. So anytime I encounter a tree, I can just jump to the root of that tree in order to continue my exploration. Now, continuing that exploration means identifying an outgoing edge and seeing where it leads me. Okay. Now, when that outgoing edge leads me to another vertex, what it's actually doing is leading me to another tree, right? And now I can link the tree I started at to the tree that I finished at, right? I can add this edge and say, I'm putting these things all together into one big tree, right? All of which reflects available capacity for augmentation, okay? And of course, once I link into this new tree, I can again jump to the root of that tree in order to continue my exploration, right? Now, eventually, that exploration will get me to the sink. And now, I'm ready to do a blocking step. Now, if we think about it, I need to know how much to block, how much flow I should send on that blocking step. And what that means is I somehow need to know well, what do I need to know in order to know how much to block? Or how much flow to send in order to block? Yes? I need to know the minimum capacity of any edge on the path that I have found. Now, this seems a little bit tricky because I jumped over the entire tree, right? I didn't actually look at these edges, so I can't explicitly keep track of the minimum. But this suggests that after I've reached the sink, I need to sort of find the min capacity on the path in the tree, right? As I've done this exploration, I've created a tree that contains both the source and the sink. So now I need to find the minimum capacity on that path through the tree from the source to the sink. Now, once I have found that minimum capacity, I need to decrease all the capacities on the path from the source to the sink. Right? That's what happens when I do that augmentation. Right? And finally, because one edge has become saturated in that process, right? That edge is no longer available for augmentation. I now have to cut that bottleneck edge. To represent it's no longer being available for augmentation. And so I've broken one tree into two trees. Okay. Now, in fact, a retreat is also a special case of this cut operation. Although not a really important one, but I can just think of retreating along an edge as cutting that edge off of the tree and moving the root back. Okay? So now we have this collection of operations, right? Oh, and also the one that I started with, jump to root or find root. Right? If I'm on a vertex, I want to jump to the root of the tree that vertex is in. Okay? So if I have these basic operations, I can implement my blocking flow algorithm, right? I start at the source, I find root, right? Once I have found the root of the source tree, I look out of the edges from that root. I find another vertex. I link to that vertex. I then find the root again and do the next link. I keep linking forward until I find the sink or I get stuck. If I get stuck, I retreat and do cuts. If I find the sink, then I find the minimum capacity on the path that I've constructed from the source. I decrease all of the edges on that path, and then I cut the bottleneck edge. So I have to know where it is, not just what is its capacity, but I have to be able to find that bottleneck edge and in order to do the decrease and to do the cut. Okay? So if I had a data structure that could perform all of these operations really fast, then I could do blocking flow really fast. Right? Because now, again, right, the find root cost, right, essentially I can associate the find root with the advance, right? So the number of find roots that I need to do is, or the find root is kind of bounded by the advance work, but we already said that the advance work is bounded by the retreat and block work. But now the block work is captured in this min capacity and decrease all operations. I don't have to touch every edge on the path in order to do the block. I just have to perform these operations. Now, obviously, this means that the representation of the capacities is going to have to be implicit, right? I can't explicitly modify the capacity on every edge because that will take time proportional to the number of edges on the path. Instead, I need some implicit representation that allows me to implicitly change the capacity of all of the edges on the path. Okay? So far, it's just been wishful thinking, right? If only there were a data structure that supported all of these operations, then I could do blocking flows really fast. So if you need a data structure, what do you do? Well, you call Tarjan. You say, I need a data structure. So Slater and Tarjan, who are the people who invented splay trees, developed a data structure called link cut trees. And they do all these operations that I just described in order log n time. Okay. So no matter how long the path is, you can find the root of that path in log n time. you can find the min capacity on that path in log n time. You can decrease the capacities of all of the edges, no matter how many they are, in log n time. Okay? And if you work through the analysis of our blocking flow algorithm, this means that you can find a blocking flow in order n log n time. Which means that you can do a max flow in order mn log n time. In other words, we can get a strongly polynomial max flow algorithm, which again is basically order mn, right? It has an extra log factor, but who cares, right? It's basically the same mn bound as the naive augmenting path algorithms. Okay? Yes? So these are trees in the admissible graph. And so the only paths that can be created are shortest paths. That's why we defined the admissible graph, right? Is that we only use these single step forward edges, right? These edges that advance forward by one layer of the admissible graph. And so any path in the admissible graph is a shortest path. Oh, absolutely. That's exactly the goal of the blocking flow algorithm, right? The goal of blocking flows is to increase that distance, increase the shortest path length. But the point is, that's what happens at the end of a blocking phase, right? A blocking phase, the whole purpose is to destroy all the paths of a given length so that, all shortest paths of a given length so that the new shortest path is longer, right? And so in this phase, right, until the phase is done, the shortest path is not changed. And as soon as the shortest path does change, that means the phase is done. Okay? All right. So how do you do this? How do you build a data structure that implements all of these wacky operations in order log n time? The answer is that you do it on top of splay trees. So you need splay trees as a starting point, and then you do this sort of goofy stuff on top of it in order to implement the operations that we need. And it gets a little bit complicated, but a quick sketch of the idea can emerge if you think about not maintaining trees, but just wanting to maintain paths as you concatenate two paths or split a path in a particular point or want to ask about the minimum value on a path. Okay, so path, you can also just think of it as a sequence of numbers, right? A sequence of capacity numbers. Okay. And again, you're going to have to use an implicit representation of these capacities. And essentially what you do is you represent the capacities as deltas. Okay, so you make sure that the value of I'm not going to store edges internally. I'm going to make sure that all of the edges kind of stay at the, no, sorry, take that back. So the value of an edge capacity is determined by the sum of the deltas on the path to the root from that edge. And here, this is not a tree edge, right? This is an edge of the path. So let me write path edge. Okay, so if you think about it, if you've got this sequence of numbers, right, you put them into a tree in the order that they appear in the sequence. So this is not ordered by number value, it's ordered by order in the sequence. And now, right, at each as you sort of work down from the, you work up from the leaves, and you store deltas in the internal nodes so that the sum of values on a path is equal to the value of the node that you're looking at. Okay? And you do this down from the root. So you can see that for each node, there's a number that you would store, which is the appropriate delta to give you the value for that number given the value for its parent, right? So you store all of these values as deltas. And now the operation of changing the value, right? So if you want to change the value, if you want to do a cut now, right, you basically need to take this whole tree and cut it at a particular spot, right? And this is one of the operations that splay trees are good at, right? We saw this split operation. For splay trees can be used to cut a path into two paths. Now, that split operation involves splaying, which involves rotating nodes, but I'll leave it to you to figure out that you can, as you do a rotation, you can update the deltas so that all of the nodes maintain their correct values, right? Nothing is changing. When you do a rotation, you're not changing the rest of the tree, so you don't have to change any of the other deltas. You just need to modify the deltas for the nodes that are being rotated, okay? So similarly, a join operation can be used to concatenate. And if you want to decrease all of the capacities, how do you do that if you're storing deltas at the nodes? Well, you just decrement the root. Right? You've just decreased, right? Every node is represented by the sum on its path, so if you decrease the root, you've decreased the capacity of every single implicit represented capacity, right? For the min, you store the subtree min at each node. Right? If each node knows the minimum capacity in its subtree, then you can compute the minimum at a given node by looking at the minimum of its two children, and that means you can maintain that as you do rotations. So it's very straightforward, actually, to design a path version of this data structure on top of splay trees. It takes a little bit more work, but less than you would think, to generalize this to working with arbitrary trees. So that's how it's done, and that gives us the mn log n time bound for strongly polynomial time bound for Maxwell. Okay. So I know that's not in as much detail as I usually cover, but I sort of set the level of detail according to the time that I think it's worth spending on this topic. Are there questions about it? Yes? The trick is that you need to maintain order. Right? I mean, there are things called union split find data structures where you can, right? Because again, we're cutting trees. We're not only joining them. But the other problem is just maintaining the order of the nodes because we have to cut off the first part of the path from the second part of the path. And that's not really part of the union find model. Yes?
We update the root value, doesn't that update all the values of the tree instead of the path of the tree?
Well, remember, so there's a tree here, but this tree is being used to represent a path. And in fact, everything that I've told, what I've told you is how to do a restricted version of link cut trees, which only works for paths, right? So what I've given you is a link cut path data structure. It doesn't allow you to make two nodes the children of the same node. Right? And for that, and because we're talking about paths, we actually choose to update the entire path, right? Part of the challenge of generalizing this to trees is that you want to only update the values on the path from a particular leaf in the tree. And so it does require generalization, but it's doable. Essentially, again, you use splay tricks to isolate the path you want to update from everything else, so that when you then perform the update, it's only getting that path. You sort of temporarily cut away the rest of the tree, so that only that path is important. Okay. All right. Other questions? Yeah, I mean, Tarjan is just amazing, right? In the amount of work that he's done, and he won the Turing Award back in the 1980s, I think, even for his work on data structures and algorithms. Okay, so where does that leave us? We now have roughly mn time algorithms for Maxflow. Okay, and this mn is actually quite natural. When we think about path decompositions, right? The very first thing we described is sort of a characterization of what's going on with max flows, right? A max flow is a decomposition of flow into, at most, m paths, right? Sorry, a max flow can be decomposed into up to m paths, and each of those m paths has length at most n. So just writing down a description of that max flow in terms of, this path uses this edges and has this much capacity. This path uses these edges and has this much capacity. It's sort of by nature a sort of an mn description of the flow, right? Now we can, once we have the flow, we can use the graph to represent it in just m, with just m numbers, the total flow on the edges. But if we want to understand how that flow is working, we need the path decomposition, and that takes the size of the description up to mn. And so this is called the flow decomposition barrier, which people thought about for a long time. Like, how could we possibly beat this mn bound, right? Now, before I go into that, I should add that sort of blocking flows are theoretically fantastic. They achieve all the best bounds that we know how to achieve. But in practice, people developed a related technique which works better, which is called push relabel. The idea of push relabel is that somehow we're being a little too rigid in defining these layered graphs and then carefully doing a blocking step to get to the next layer graph. And each layer, we sort of use a breadth first search to recompute the distances and so on and so forth, right? In push relabel, instead of having this notion of separate phases, you have local updates to both flow and distance. You define something called a preflow, which sends flow to all the vertices, not just the sink. Okay, so your preflow may leave excesses at some vertices. So balance is not satisfied. Okay, there can be more flow coming into a vertex than going out. Okay. The idea of the push relabel algorithm is to combine a push step and a relabel step. A push step moves excess to a neighbor that appears closer to the sink. And I say appears here because you don't work with the actual distances, you just work with your current distance estimates, which are kind of like the distance estimates in Dijkstra's algorithm, that they're like upper bounds on the distance, but they might not be accurate. Okay. A relabel is used and says, if you have no closer neighbors, then you have an indication that your distance is wrong, and you sort of increase your distance. Okay? And so the push-relabel algorithms do a sort of arbitrary combination of these operations. If there's a vertex with excess that can push to a neighbor because that neighbor is closer to the sink, well, then you do it. And you've moved some flow towards the sink. If there is no such neighbor, then you raise the distance of that vertex, and that is now going to put it farther away from some of its neighbors so that now it becomes possible to push some flow apparently closer to the sink. And you keep on doing these operations until, in fact, your vertices have gotten such large distances that they're farther away from than the source, and then the excess that remains gets pushed back to the source. And that's how you take care of getting rid of the excess. And eventually, there's no excess anywhere, and then you have an actual max flow. Okay? So it's using these same ideas as push-relabel, as blocking flows, but it's not doing these sort of large phases of exactly computing the distances and then exactly computing the blocks. And this creates an opening for lots of heuristics about which vertex do you push from, when do you relabel, and so forth. That leads to lots of better time bounds than the blocking flow algorithms, and in fact, leads to near linear time performance in practice. Okay, so max flow can be solved really, really fast in practice using push-relabel techniques. Okay, but push-relabel still suffers from this path decomposition barrier, which stuck around for a long time. In the 90s, I think, and the 2000s, there was some progress on, I guess, 99. Goldberg and Rao figured out how to take the special bounds that we got for unit capacity graphs, the m to the 3/2, right? And they generalized them to capacitated graphs. Turned out to be very difficult, but they pulled it off. And so this breaks the flow decomposition barrier, because in capacitated graphs, it is not necessarily the case that you can get by with square root of m distinct paths. Nevertheless, they have an algorithm that beat it. Also, mn to the 2/3 log u. Okay. But the big breakthrough in MaxFlow, which emerged in the 2000s and 2010s, is one that actually makes me kind of sad, because the real breakthrough was through the use of linear algebra. And I don't like linear algebra. I mean, I took an extra week of spring break during my freshman year, and that's when they taught linear algebra, and so I missed it, and I never really it never really agreed with me. You know, MaxFlow is this beautiful combinatorial problem where you get to talk about paths and think about water flowing through pipes and so on and so forth, and that drove the field for many decades. But in the 2000s and 2010s, people started thinking about MaxFlow as a linear algebra problem. And in particular, they focused on electrical flow. So the idea here is that if you make an electrical network out of a bunch of resistors, and you put a voltage at a source and a ground at a sink, then there will be current flow through that electrical network, right? And that current flow is determined by a bunch of linear equations. Okay? I should say the S to T current flow as a function of the resistances. And so computing the current flow involves basically solving a large linear system. And this is a very special linear system. And over time, people have developed super fast solvers for it. Okay. Now, it's not clear that you can immediately use this for max flow because there's no capacities in an electrical network, right? The current can be infinite depending on the resistances, right? So how do you enforce capacities? Well, to enforce capacities, what you do is you solve your electrical flow. And then you notice that some of your edges are carrying too much current, right? What should you do about that if you want them to carry less current? Yes?
Increase the resistance?
Exactly. You increase the resistance on oversaturated edges. And now you compute a new flow, and you've just sort of encouraged the flow to go away from those edges. Now some other edges might get saturated, so you increase their resistance. You have to be very careful about this, doing it just right. Actually, one of the leaders in this work was Alexander Madry, who's a professor here. So in 1913 and 16, he was able to use these techniques to get an order m to the 10�7th log u runtime, okay, which beats the m to the 3/2. And then some of his students, Lee and Sidford, in 14, I think, they managed an order m square root of n log u. These techniques are all scaling. There's always a u, or they often talk about it as an epsilon, like you get within epsilon of the max flow, instead of assuming integer values, which doesn't make a lot of sense in linear systems. They just talk about getting within epsilon of the max flow. But of course, if epsilon is 1 over u, then for an integer problem, you've gotten within 1 of the optimum. But the real breakthrough just happened this year. It's a group of 6 people, Chen et al. And this is a paper that solves max flow in order, I think, m to the 1 plus epsilon time for epsilon as small as you want. Okay, so near linear time. And it's only 109 pages, this paper. So if you want to find out about the current, the current state of the art in max flow, just go to archive.org and give that a read. Okay. And so for me, this is an unsatisfactory state of affairs because I feel like these linear system approaches are ignoring the sort of natural combinatorial nature of the problem and basically taking a sledgehammer to a very delicate vase, right? And so I would like to see somebody kind of retaliate with some beautiful combinatorial algorithms that maybe use these insights, but give you, but that also map to more of our intuitions about how max flow is what kind of problem maximum flow is. Okay, I don't think that these techniques are yet practical, but I suspect that they will be. At the moment, I think most max flow problems are still solved using push relabel. I don't have time to tell you more about push relabel now, but after Thanksgiving, when I'm no longer doing the required lectures where there's homework, right? After Thanksgiving, there won't be any homework anymore, and so I'll just lecture on whatever I feel like, and I could do a lecture on push relabel if that's a topic that people find interesting. Okay. But that's the end of the story for max flow. Are there any final questions about it? So again, the big story is, as you started to see in your problem sets, max flow can be used to solve all sorts of problems that don't look like max flows on the surface. And we have fantastic algorithms for them in practice, as well as that emerged from a lot of deep theoretical work. So that's why it's such a central topic in combinatorial optimization. Yes?
Is there no log factor?
That's inside of the 1 plus epsilon, right? So the point is that this is probably changing by the day as they kind of refine, because this paper was only published in like April or something. Last I looked, I think that, right, that epsilon could be any constant value that you want. So it could be like m to the 1.1, but that's going to swallow up any log factors in like m to the 1.05 log n or something like that. Okay. I'm sure there's lots of logs, right? But they're just hiding. Anything else? OK, then let us take a short break, and then we will start min-cost flow. Let me check. They should be coming back very soon, but let me just double check with them. Yeah, what's the status?
Yeah, one is finished. I was wondering what we're doing about solution.
All right, so starting some logistical things. Problem set one is graded, and we will get that back to you as quickly as possible. I think pset 2 is probably also graded at this point and can come back. So you'll start to see the psets coming back in rapid succession now, and we'll get the solutions posted as well. On Wednesday, I will not be here because of Yom Kippur. So we will do the recorded lecture game again. We will post information about what recordings or what combinations of recordings you should watch. You can come here and watch them with the TAs who will pause them for questions if you have them, or you can watch them at home. It's up to you. That lecture is where we'll finish up min-cost flow and probably start linear programming, which will be the next topic. But for today, let me introduce you to min-cost flow. Whoops. So min-cost flow, and it's actually implicit that it's a min-cost max flow. So the idea here is that you have a flow problem, a max flow problem. But you also have, for every edge E, it has a cost C of E. And so this is why we couldn't use C for capacities, so that we needed it for costs. Okay. And now the value of a flow is just the sum. Notice that this is a per unit cost. So if you send twice as much flow, it costs you twice as much. Okay. And our goal is to find a flow of minimum value. That is a max flow. Okay. Now, in min-cost flow, it really tends to be easier to work with the gross flow formulation, in which the flow on edge E is equal to minus the flow on E reversed. Because otherwise you start double counting things in the net flow version. And so, I mean, in your summation, you're not summing over an edge and its reversal. You're treating the edge and the reversed edge as the same, right? And so if you have 2 units of flow in one direction, then it gets multiplied by the cost of the flow in that direction. That is very consistent with the idea that the cost of the reversed edge is just minus the cost of the forward edge. Okay. We are basically going to recapitulate. Oh, and also notice, I will say, the C's can be negative. So when you're modeling certain problems, it makes sense to talk about the profit that you earn by sending flow along an edge instead of the cost that you pay by sending the flow along the edge. And of course, they can be 0 as well. Okay. So we are going to recapitulate a lot of what we did with max flow. We're going to talk about sort of structural characteristics, and then we're going to use that in order to think about how we can know that a given flow is a min-cost flow, right? And after that, we will start saying, well, and if we can know that a flow is not a min-cost flow, is there an algorithm for improving that min-cost flow? And does that lead us to an algorithm for actually doing a series of improvements in order to actually compute the min-cost flow? So much like what we did with max flow. So in particular, for starters, notice that flow decomposition still holds. And in particular, that means that the cost of the flow is just equal to the sum of the path and cycle costs in the flow decomposition, right? Of course, you also need to pay attention to the amounts, the capacities of those paths and cycles when you're talking about the overall cost. Okay. Now there is one way that min-cost circulation actually simplifies compared to max flow. Min-cost flow simplifies with regards to compared to max flow. And that's through a kind of more elegant formulation called min-cost circulation. Okay. So a circulation is basically a flow with no source or sink. Okay. So it has balance everywhere. every vertex has the same amount of flow entering and exiting. Okay. Now, when you're talking about max flow, it doesn't make sense to talk about circulations because, I mean, there's no point in having a circulation. It's not moving flow anywhere, right? But when you talk about min-cost circulation, it does, right? If there are, for example, profits on some of the edges, then you might be able to make money by sending flow through those edges to give you a profit. Okay, so there's an interesting problem of constructing a min-cost circulation. Okay, and a circulation is more elegant than a flow. We talk about flow decomposition into paths and cycles. What's the decomposition of a circulation? Right, if you run our flow decomposition algorithm on a circulation, what do you get? Yes, only cycles, right? If you go back and look at the decomposition algorithm, the only way you get paths is if you get stuck at S or at T. And there is no S or T in a circulation. So you'll just, you'll traverse the circulation until you get back to a vertex you've seen before, and that gives you a cycle. And you just keep peeling off cycles, right? So this is already more elegant, that you don't need to talk about paths at all, but only about cycles. Okay. So let's talk about the relationship between min-cost circulation and min-cost flow. So suppose I want to do a reduction. Suppose that I have an algorithm for min-cost flow. Sorry, this not doing well with the chalk today. Suppose I have an algorithm for min-cost flow, and I want to use it to solve a min-cost circulation problem. Okay, so here's the min-cost circulation problem I want to solve. I need to give the min-cost flow algorithm a flow problem. There needs to be a source and a sink, right? So how do I do that reduction? Yes?
Put on a source and a sink and not connect to anything.
Exactly. Just add a disconnected source and sink. So the value of the min-cost flow in this graph is going to be 0, right? You can't, the amount of flow is going to be 0. However, the min-cost version of that 0 flow may and will send a minimum cost circulation through the network. Okay. What about the other direction? Suppose that I have an algorithm for min-cost circulation, and I want to solve a min-cost flow problem. So here's my min-cost flow. It does have a source and a sink. How do I transform that into a circulation problem that I can optimize? Yes?
Really low.
Exactly. So I take my circulation problem, or sorry, my flow problem, which has an S and a T, right? And what I do is I add an edge that goes from S back to T and has a cost of minus infinity. Okay. And also has an infinite capacity. Okay, so what is the effect of this going to be when I solve a min-cost circulation problem? Well, in order to achieve minimum cost, when you have an infinite profit on a particular edge, you're going to send as much flow as possible through that edge, right? And that is going to force you to send as much flow as possible from S to T in order to be able to ship it back along the return edge. Okay. However, since you're aiming for minimum cost, the way that you are going to ship the flow from S to T is along the minimum cost flow from S to T. So the dominant constraint is that you have to send the maximum possible flow in order to earn the minus infinity cost. But among the different ways to send the maximum possible flow, you're going to choose the minimum cost way, because that's going to give you the minimum cost circulation overall. Okay? Yes?
The reduction to min-cost flow.
This one. Yeah, so for that one, the idea is you're given a min-cost circulation problem, right? Find me the min-cost circulation. All you do is you create a vertex S that you call the source and a vertex T that you call the sink, and you say, find me the min-cost max flow in this network. Okay? Now, the maximum flow in this network sends 0 flow from S to T because there's no way to send any. However, it is also aiming to minimize cost. And so the value of that flow is determined by, where did I write it? Over here, right? This quantity, right? Which is essentially going to be measuring the cost of the flow that's circulating in the network aside from S and T. Okay? So you already know what the value, what the amount of flow is going to be, but the min-cost flow algorithm is still necessarily going to compute a min-cost circulation in order to get the minimum cost of those value 0 flows. Okay? So, okay, other questions? All right. We don't like to work with minus infinities. They're hard to store, right? So do these numbers actually have to be minus infinity in order to make this reduction work? Or can I get away with some finite numbers that would still have the same effect? Yeah?
The multitudes larger than all the other numbers in the problem?
Yeah, so it feels like I should just be able to make these numbers larger in magnitude than all the other numbers. But like, I mean, in here, we might have a maximum capacity U and a maximum capacity C, right? Can we just make these like minus C and U? Will that be enough? Yes?
We need to do like the sum of U and sum of C.
Exactly. So in terms of the capacities, we'll just use M times U, right? That guarantees that however much, the maximum amount of flow that can possibly move from S to T is M times U. And so this capacity makes enough for all of that flow to get back from T to S, right? Now, in terms of the cost of the flow, right? Well, if we think about the path decomposition, right? The cost of each unit of flow going from S to T is at most n times the largest possible cost, right? The cost of most n times c. So if we set the cost here to be minus n plus 1 times c, then that's going to overwhelm whatever positive cost is in the other part of the cycle. And as we will shortly see, that's enough to force the min-cost flow to come out the way we want. Okay? All right, so that's a nice simple reduction, but it does have one unsatisfactory aspect, which is that if, for example, we're working with a graph with unit costs and unit capacities, and we do this reduction, all of a sudden our costs and capacities are m and n, right? And we've already seen how unit costs and capacities are often a lot simpler and have better algorithms. So introducing capacities where you don't need them is potentially a problem. So let me point out another reduction. Okay. The idea is, given a min-cost flow problem, let's just consider any old flow. Max flow, rather. And also let's consider the min-cost flow, which is also a max flow, F star. Okay. We know how to compute a max flow. The problem is that we want to compute the min-cost flow. But suppose that we have computed the max flow. What is the difference between the flow that we have and the flow that we want? And let me ask that literally. What is the difference F star minus F? Okay, so you can talk about this on an edge-by-edge basis, right? You take the flow that F star is sending, and then you subtract the flow that F is sending on that edge. If it's sending it in the opposite direction, then it actually turns into an addition of flow, right? So if I do that, what do I get? Yes?
Should be a circulation.
Exactly. Right? If you think about it, subtracting F is like adding the reverse of F. Right? What is the reverse of F? It's a max flow from T to S in the reversed graph. Right? So basically, subtracting F, right? F star sends a bunch of flow from S to T. Subtracting F sends all that flow back from T to S. And so overall, you get a circulation. Right? Another way to say it is that you get balance everywhere. Right? Because the only difference, because F star and F have the same excesses at S and at T. Okay? And so they cancel out. Okay. So the difference between any two max flows is a circulation. Another thing to note, to observe is that this circulation is feasible in the residual graph that you get from F. Okay? Because the residual graph that you get from F subtracts F sub E capacity from every edge E. And that matches the subtraction of F sub E flow that you're taking away from F star. So, right, F star is feasible in your original graph, right? Now you're subtracting F units of flow from every edge that F star is carrying, and that makes it feasible in the residual graph because the capacity that you subtracted from F is exactly the amount that you're subtracting from the capacities as well. Okay? And so put this all together, right? The story that we have is that the difference between any two flows is a min-cost flow, is a circulation. And the difference in cost, right, is, of course, the cost of F star minus the cost of F. That is the cost of the circulation. Right? And so, in particular, what that tells you is that let's see, how do I want to say this? Yeah, so basically, if you find any F star, right, this is not only true about the min-cost flow, right? If you consider any other flow, right, the difference is feasible in the residual graph, and the cost of the difference, the cost of the circulation, is just the difference in cost of the two flows. And so what that tells you is that the min-cost flow is just equal to F plus whatever the min-cost circulation in the residual graph of F. Okay? So this is a different reduction, but in order to find a min-cost flow, you just find any old max flow, and then you turn it into the min-cost flow by adding a min-cost circulation in the residual graph. Okay? And this just follows from the linearity of all of these objective functions. Okay? And the nice thing about this is that you're just working with a residual of the original graph. So if the original graph had unit capacities, the residual graph will have unit capacities, and so you're doing all of your calculations of the min-cost circulation or whatever under the same constraints as the original graph had. So we can really focus our attention on finding min-cost circulations, and for a lot of this topic we will. There are other times, though, where it's useful to go back to talking about min-cost flows. And so we'll do that when it's suitable. So the next step in our path is to think about verifying optimality. So we are given a max flow. How do we know it's a min cost flow? Yes?
All of the cycles and see if any of them have a negative cost.
All of the cycles in what?
The residual graph.
Okay, so your claim is that it is a min cost flow if there are no negative cost cycles in the residual graph. And that is correct, but let's creep up to it. Okay, how do we show that? Okay. So the optimality condition that we actually have, we can pull out from this reduction, right? So if your flow is actually the min cost flow, what can you say about the min cost circulation in the residual graph? What is its cost going to be? Yes? Not positive. Let's be careful about that. So if the value of the min cost circulation in the residual graph is positive, then that's saying that the min cost flow has value not bigger than your flow. So I think you actually have to invert that, right? So the point is that if f is the min cost flow already, it has to have the same cost as whatever hypothetical min cost flow there is. So in fact, the value of this min cost circulation will be what? 0, right? So f is the min cost flow if the min cost circulation in G sub f has value 0. And this is an if and only if, right? But what does it mean for the value of the min cost circulation to be 0? Well, now we can imagine decomposing this into cycles, right? And what can we say about those cycles in this min cost circulation in the residual graph? Yes? If the graph is capacitated, they might not be edge disjoint, right? Because you could have two cycles that are both going through the same edge using some of the capacity of that edge. Right? But what can we say about the cost of those cycles? Yeah?
None of them can be negative, or else the cost of the min cost circulation would be negative.
Right, right. If any are negative, then that gives me a single cycle is a circulation. And so you could use that negative cycle to create a negative cost circulation, which would violate the optimality of your flow. Right? Another way to look at that is to say, well, if I had a negative cycle, if I sent flow around that cycle, I would still have a max flow, right? But it would be cheaper. Okay? So if there is a negative cost cycle, then the flow is not a min cost flow. Right? Now, what if there is no negative cost cycle? What does that imply? Yeah?
0.
Why?
Oh, we can, the minimum cost is not to do any cycling, so 0.
Right. That means, right, that if whatever your circulation is going to have non-negative cost, because the circulation decomposes into cycles, right? And that means that the min cost circulation is no circulation, which has 0 cost. And that means that your flow is a min cost flow, according to that condition that we were looking at. So we have now an if and only if, right? A given candidate, a given max flow, remember that it has to be a max flow, but it is optimal if and only if there is no negative cost cycle in the residual graph. Okay. So this actually immediately suggests our first algorithm for min cost flow. What should we do to compute a min cost flow? Or actually, thanks to our reduction, right? To compute a min cost flow, we find a max flow, and then in the residual graph, we compute a min cost circulation. So what should we do in order to compute a min cost circulation? Up here, we have identified a condition that tells us whether a given flow or circulation is optimal, namely that there is no negative cycle in the residual graph. So how do we compute a min cost circulation? Well, the first thing to do is to look and say, OK, is it optimal? Great, we're done. OK, it's not optimal. There's a negative cost cycle in the residual graph. What should we do? Yeah?
Like by, I mean, just by putting flow through it?
Exactly. So this is known as Klein's algorithm because, again, if you were alive in the 1960s, you got the most obvious algorithms in the world named after you, right? So while there exists a negative cost cycle in the residual graph, saturate it. In other words, you find the minimum capacity edge on that cycle, and you send that much flow through the cycle, which makes the residual capacity of that min cost edge 0, so you've destroyed that cycle in the graph. So you just killed that negative cost cycle. Okay? Now, of course, this might create other negative cost cycles, right? Because you're creating edges, you're creating residual edges as well as destroying them. Okay? But I claim that this is making progress, right? And let's focus on the integer case. Okay. So if all of the costs and capacities are integers, right? What sort of progress can we say we're making when we saturate a cycle? That is, when we saturate a negative cost cycle? Yes?
You've at least reduced like the total cost by 1.
Exactly, right? We are sending at least 1 unit of capacity. Right? Through, at most, -1 cost, because the cost of cycles are integers and it's negative, so it's at most -1. So we decrease the cost by 1. So how often can we do this before we must have a max flow, or so before we must have a min cost circulation? Well, can we just lower bound the cost of a min cost circulation, right? Once we get past that lower bound, we know we're done, right? So what is the cheapest possible min cost circulation in a graph with the given upper bounds on cost and capacity? Well, in the very best case, if you're trying to get as cheap as possible, right, every single edge will have cost minus C, right? and have capacity U, and you'll be able to saturate all of the edges in order to get all of that cost in your min-cost circulation, right? So the cheapest possible circulation is minus MCU, right? And the most expensive possible, by the same reasoning, actually you're going to start with a 0 circulation, so let's just leave it at that. And that means that MCU iterations suffice to find the min-cost flow. Now, what does an iteration mean? What do you have to do in an iteration? Well, you have to check if there's a negative cost cycle. How can you do that? We haven't really talked about cycle detection algorithms. Right? How do you decide if there's a min-cost cycle in a network? Yes?
You can compute all the cycles and the costs of all of them.
That is true. You could compute all of the cycles. The only problem is that there could be like m to the nth power cycles or something, or n to the mth power or something like that. So that's going to be an exponential time algorithm. Yes? Bellman-Ford. So the trick is to associate this with shortest paths. Okay? So we know all sorts of algorithms for shortest paths. And if you think about it, shortest path algorithms make sense unless a graph has a negative cycle, right? If there's a negative cycle in a graph, what does that do to the shortest paths? They become negative infinity because you can have a path that just goes around the cycle as much as you want and gets as short as you like, right? So a negative cycle can be detected by discovering that there are no well-defined shortest paths. And it turns out that basically all of our shortest path algorithms will scream an alarm if there are no shortest paths, right? We have these correctness proofs, but the correctness proofs depend on the existence of shortest paths. And so the algorithms become incorrect if there's a negative cycle, and their incorrectness manifests in a detectable way. Okay? Now, that means you can use any shortest path algorithm to detect negative cycles. However, remember that we're talking about graphs with both positive and negative edges. So the obvious candidate, Dijkstra, doesn't work because Dijkstra only works for positive edges. But you can use Bellman-Ford, a well-known algorithm for shortest paths. And it has a running time of order mn to compute shortest paths, but also to detect a negative cycle. You put these together, and you get a running time for Klein's algorithm, our first min-cost flow algorithm, of order m squared n times cu. Yes?
Aren't we doing, like, aren't they less connected? Should it be like plus instead of times?
Sorry, what's that?
Because in every iteration we find the negative cycle and we fix it.
That's right. Each iteration is find that negative cycle and then push flow around it to destroy it. Now you find another negative cycle, push flow, right? So mn per cycle detection and saturation, and you'd have to do MCU of them. So this is the runtime of Klein's algorithm, right? This is already what we were paying for MaxFlow. And here's an additional CU cost. So this is a pseudo-polynomial algorithm. It's not even weakly polynomial. And the rest of min-cost flow, which we'll cover on Wednesday, is about how to achieve polynomial time using deeper insights into the nature of min-cost flow. So that will have to be by recording. Then you should look for a problem set to be posted as well. Since I'll be able to look at the recordings to see exactly how far I'm going to get, I should be able to post the p-set before Wednesday. So it'll be ready for you whenever you want to start tackling it. Any final questions? OK, then I will see you on Friday.